Good evening, everyone. Welcome to the 9th problem solving session for the course Structural Analysis. Let me start sharing my screen. So today we'll be looking at the displacement method of analysis. The past few sessions, we have been looking various methods to analyze statically indeterminate structures. So we have been doing analysis of statically So the three key concepts that are involved in the analysis of statically indeterminate structures are: one is the equilibrium equations. Another way to say that the solution that we get satisfies the equilibrium conditions is that it is statically admissible. The second condition is compatibility, which basically means the deformation that we get or the deflected shape that we get is kinematically admissible. And the third condition is force displacement relations. Which is also known as constitutivity. So we have seen force methods of analysis. So what did we do in force method of analysis? We constructed a primary structure which is statically determinate and stable, and determine the unknown reactions using the compatibility conditions. So in force method of analysis, forces were unknowns. But the force system that we considered was automatically satisfying equilibrium and the force displacement relations. In addition, whatever additional forces that we could not determine, for that we used the compatibility conditions. So whatever forces, so suppose we had a prop cantilever subjected to some loads, whatever primary structure that we got, this primary structure, both of them were statically admissible. Why? Because after replacing the unknown reaction with a redundant, we enforce the equations of static equilibrium to determine the support reactions and the bending moment diagram. Then finally we superimpose both to enforce our compatibility conditions. So in the force method of analysis, the basic idea is we choose a force system that is statically admissible, that satisfies the equilibrium equations and the force displacement relations automatically, and whatever unknowns are left, we determine those unknowns by enforcing compatibility. On the other hand, in the displacement method of analysis, which we'll be seeing today, the primary unknowns are displacements. So here, what forces were unknowns? Either the member forces or reactions. So similarly, we know that the displacements are unknowns, but where are the displacements found? They are called nodal displacements. We'll come to it. And in this method, the fundamental difference is we construct a kinematically admissible displacement field. That is, we have a displacement field which satisfies the compatibility conditions and the force displacement conditions. And whatever unknowns are left, those we enforce by using, those we determine by enforcing the equilibrium conditions. So this is the subtle difference between the two methods of analysis. Ultimately, we have to use all the three conditions, which is equilibrium, compatibility, and constitutivity. But in the force method, we construct a force system which is statically admissible and then enforce the compatibility conditions to determine the unknowns. But in displacement methods, we construct a displacement field which is kinematically admissible, and then we use the equilibrium equations to determine the unknown displacement variables. Now, I said displacements are found at the nodes. So in a skeletal structure, so we have some structure like this. This is a statically indeterminate structure. It is also a kinematically indeterminate structure. So what is kinematic? So suppose I know the displacements of this point, this point, this point, and this point. So wherever we have a connection between two or more members, we call those points as nodes. So what are either there's a connection or a support, or sometimes even we can consider those points where there is a abrupt change in cross section. Abrupt change in say some properties EI or. So if we know the displacements of those points, we can determine the displacements anywhere in between the in between them using the equilibrium equations. So we know how to determine the bending moment diagram, and once we know the bending moment diagram, we can use the force displacement relations to determine the deflected profile of the beam in between. So the fundamental unknowns in the displacement method are the displacements and rotations, right? So displacements and rotations at the nodes. There's a special name to these displacements and rotations. They are called degrees of freedom. So what are degrees of freedom? We have seen this already. Degrees of freedom are those variables that completely specify the configuration. Configuration of the structure. So in this case, if we know the degrees of freedom, if we know the displacements and rotations of each point in this structure, then we can determine the complete configuration of the structure. The configuration means all the displacements, all the rotations, all the internal forces, all the shear forces and bending moments anywhere in the structure. So that's basically that. Now, why do we need the displacement method of analysis? Because we have been using the force method of analysis quite often. Now, what was the need that this displacement methods of analysis got developed? So why? Why displacement method? So if you recall, one of the major issues is that once we draw in statics, right? So drawbacks of force method. So if you recall, if we have some structure which is statically indeterminate, we construct a primary structure which is statically determinate, and then determine the unknowns by any we use the principle of virtual work. But when we use the principle of virtual work, if you recollect, we got a matrix which is called the flexibility matrix, F11, F12, and so on in general. In this case, it is only a two, it is statically indeterminate to the second degree. So in general, this matrix can be as large as it can, as many. So the size of this matrix is as many redundant forces as they are, times x1, x2, and so on is equal to d1l minus of d2l. And the issue is this matrix is densely populated. That is, except for some special cases, these coefficients which we determine as Fij is integral mi mj by ei dx. In general, this is an integral, and this Fij is not zero in general. So if we have a So this matrix is particularly very dense. So the force at any point in the structure will cause a displacement anywhere else. So this, what is called as flexibility matrix, is very dense. Very dense meaning it is densely populated. There are not many zeros. So computationally, it is not very efficient. Once the size of this flexibility matrix exceeds, say, 4 cross 4 and above, solving this manually is almost impossible. So it takes a lot of time. So solving 5 cross 5 simultaneous linear equations is very difficult. So that is one drawback of this method. And what is the other drawback? So this one, what it says is when the size of the system, when static indeterminacy is very high, this is a dense matrix of size ns cross ns, and it becomes very difficult to solve for. That is one difficulty. And the other issue is programmability. Now note that once you have determined the primary structure, we'll get ns number of redundant, ns number of primary structures plus redundant forces, and one structure which is the primary plus applied load. Now in each of them, we are expected to determine mi of x and capital Mi of x, capital M of x is my. Now this is not a programmable task. So why is it not programmable? So suppose this is a primary structure, right, with some load distribution. We are required to determine the bending moment throughout this. So that requires taking a section at some point and finding the distance. And so all this is in general not a programmable task. So, for each of them, we need to satisfy equilibrium, which is a very difficult task in general. So if you have a full multi-story structure, taking each beam, so a multi-story structure is statically indeterminate to a very high degree. Constructing primary structures, redundant structures, and then analyzing them, right? When you have a big multi-story structure, and say, suppose you cut this off, and you release some reactions, and then analyzing it is a very difficult task. So that cannot be programmed in a computer in a general sense. So that is one difficulty. On the other hand, in the displacement method, so ensuring that each of the primary structures satisfy equilibrium equations is not an easy task. But ensuring that each of the primary structures satisfy the kinematic admissibility, that is, enforcing compatibility, is quite easy. So if you have a beam like this, which is continuous over some support, subjected to some loading. So this is also statically indeterminate to second degree. Now enforcing that each segment of the beam satisfies equilibrium is difficult, but compatibility is quite easy. So suppose this point is A, B, and C. What is one compatibility equation that we can think of? That is theta A to the left is the same as theta A to the right. Similarly here, theta B to the left is the same as theta B to the right. And here, what are the compatibility conditions? Theta C is equal to theta delta C is equal to 0. So these are fairly easier to enforce in a computer than enforcing the equilibrium conditions. So this is the main motivation why these displacement methods of analysis have been developed, and it has been quite successful. So basically, displacement methods of analysis started with the slope deflection equation. Displacement methods of analysis started with the slope deflection equation. Then they developed into the direct stiffness method, something called the direct stiffness method for structures. So this further got developed into the finite element method, which is a very powerful tool, which is widely used in the industry and in research for various nonlinear and linear static and dynamic analysis. So this forms the basis for all the advanced analysis techniques that we use today, both in industry and in research. So let's quickly look at the steps for this slope deflection method. Before we get to that, there are certain sign conventions that are important, as usual, as with any method that we have done so far. So sign conventions are as follows. We have a beam continues over many spans and have something like this. So this is statically indeterminate to a very high degree. So what is ns for this? It is you can say 3 plus 1 plus 1, which is 5. What is the kinematic indeterminacy for this beam? So here there are no free degrees of freedom. Here there are no free degrees of freedom. I have already said that kinematic indeterminacy is nothing but the number of degrees of freedom that we cannot know. So these are already specified. So at this end, we know the degrees of freedom, they are 0. Here we know they are 0. Here what is unknown? Here the slope is unknown. So in case 2. So this such a problem, it is easier to solve using the displacement method of analysis, because here you will get a 2 cross 2 system which needs to satisfy the equilibrium. Here you will get a 5 cross 5 system, which is obtained by satisfying compatibility. Now suppose it is subjected to some loading. How does it deform? It deforms something like this. It deforms something like this. Something like this. So the primary unknowns here are the rotation at this joint and the moments that are occurring. So if you isolate this joint is subjected to some moment. Similarly, this joint is also subjected to some moment. Now, the sign convention for the moments in this method is all clockwise moments and rotations are positive. And displacements that cause positive chord rotation are positive. So what is positive chord rotation? Rotation means clockwise. So if they're also positive. So suppose I have a multi-span beam and say this support is settling by some delta, then how does this beam deform? It deforms something like this. Something like this. So in the deformed beam, let me draw an exaggerated view. This is where the support is, and this is where the fixed support is. This is called a chord. So this is the chord. And in this span, let me call this A, B, and C. And in the span AB, this delta has resulted in a clockwise rotation. So in this span AB, delta should be taken as positive. On the other hand, when we write the slope deflection equations for the span BC, this chord has rotated in a counterclockwise direction. I hope you can see that this chord has rotated in a counterclockwise direction. So in this chord, the same delta is negative. So in span AB, this chord has rotated by a clockwise angle theta. In the span BC, it has rotated by the same angle. If this is same as both are of spans L, this has rotated by the same angle theta, which is nothing but delta by L. But in this case, when you write the moment slope deflection equation for this span, delta should be taken as negative. So that is the sign convention. Now, what are the slope deflection equations? So slope deflection equations are written for one span, just like the Clapeyron's theorem of three moment. Unlike the method of consistent deformations, here we always consider one span at a time. So let me write it down. So if we have a multi-span beam like this, subjected to some loading, have a moment. So if I take span AB, I can also continue this side. Have some E. So if I take span AB, the slope deflection equations are as follows. The moment AB, what is MAB? MAB is the moment in the span AB at A. So that is, if you cut this beam here, this is MAB. If you take this point, and this is MBA. So MAB is given as 4 EI, and say this beam rotates this way. So this side it has rotated by theta A. Here it has rotated by theta B. Both are in the clockwise direction. So it is 4 EI by LAB theta A plus 2 EI by LAB theta B minus 6 EI by L square delta. So I've already said how we take the sign convention for delta. Is that all? So what this relates, you can see. So it relates the rotations at the joints to the moments that are generated at the joints. So this MAB, what is the moment generated in the span at the joint A, is a function of the rotation here, it's a function of the rotation here, and it's also a function of the relative displacement. But what have I forgotten? So I've left the load here, right? So that the effect of the load is taken care by the next term, which is, you can call this as M. Yeah. So this we can call as F. So how is this derived, right? Professor would have derived it in his lectures. Let me just give a sketch of what is that. So basically it follows superposition. Suppose we have the span AB deforming in all possible ways. So this is the initial undeformed configuration. And after deforming, it goes to something like this. So the chord has rotated by some angle. There's a moment acting here. There's a moment acting here. And this is delta. This is theta A. This is theta B. Now the steps are, so we have a lot of things here. So we need to consider the effect of, and we are also having some loads. So we need to consider the effect of the displacement, the rotation here, and the loads. So that is very simple. So first, so the first structure that you considered is fix both the ends and apply specified loading. So it will generate what are called, the fixed end moments, MABF and MBAF. Suppose there is no rotation, then there will be fixed end moments. So if we have a fixed beam and subject it to some loading, there will be some end moments that are generated. So that is one part of it. Superpose this with the second case, remove the applied loading and allow the beam to rotate by some theta A. So here, if you rotate this side by some theta A and hold this side fixed. So in this case, you will need some moment, right? So this will be, say, let us call it MAB1. So this is what is called caused by a rotation of theta I. So if you fix the far end and you apply a rotation here, what will be the moment that is needed to rotate the beam at this point by an angle theta I? So that is this. And what is the value? It is easy to see that if you use, say, the conjugate beam method or the moment area method or the principle of virtual work, you can easily determine the moment that is required to cause this rotation is 4 EI by L theta A. And what will be the moment that is generated here? Always note the direction of the moments. I'm taking all the moments in clockwise direction. So that is very important. Here, let me call it MBA1. That is nothing but 2 EI by L theta A. So if the far end is rotated by theta A, there will be a fixed end moment that is generated here. And that is equal to 2 EI by theta A. What is the next condition? So we have considered the load first. We have considered this theta A at once. Then what you should do is fix theta A. So fix theta A at 0 and rotate the other end. So the other end, if you rotate something like this. So this has rotated clockwise by theta B. And to cause this rotation, you need to apply a moment, say MBA2. How much is that? It is exactly identical to this situation, only that the sides are interchanged. So this is nothing but 4 EI by L theta B. And because of a rotation here, the beam is strained, right? The beam is strained everywhere. So that strain will also pull against the support and generate a moment MAB2, which is equal to 2 EI by L theta B. And what is the other thing that we have left out, which is the relative displacement. So now fix theta A is 0, fix theta B is 0, and don't apply any loading. Now we'll consider the effect only of the displacement. So as I said, the displacement, if it is rotating the chord in a clockwise direction, it is positive. So this is what we should consider. This is delta. You can see the chord has rotated in the clockwise direction. So in this case, again, the beam gets strained, right? The beam material will get strained everywhere. So here you will have a moment of, you can easily see the moment will be in this direction. So it is anti-clockwise. So I have to put so actual moment will be like this. It will be a hogging moment, and this side it will be a sagging moment. But we should be consistent with the clockwise sign convention. So here you have a moment of minus 6 EI by L square delta. So we have also seen this term in the Klepperov's theorem of 3 moments. Here you will have a clockwise moment of, again, you will have a counterclockwise moment, but you have to be consistent with the sign convention. So it is minus 6 EI by L delta. So let us call this MAB3. This is MBA3. Now, what is the total moment? Just use the principle of superposition. You're considering one force, one rotation at a time, then add them all up. So that is basically this. So if you fix the end, because of the applied load, something will happen. In a general beam, there is also a load. There is also rotation here. There's a rotation here. And also there can be some support settlement. So finally, the equations that we get are, use a different color. The equations that we get are MAB is 4 EI by L theta A. Just add them all up. Plus, because of a rotation theta B, the moment that is generated is 2 EI by L theta B. And because of this rotation, chord rotation, you have minus 6 EI by L square delta plus the fixed end moment with the appropriate sign convention. And similarly, MBA will be, if I write it in the same form, 4 EI by L theta B minus 6 EI by L square delta plus MBA. And here you will have A. So 2 EI by L theta A. Now this you write down for every span. So for this span, you will have an MAB, MBA, MBC, MCA, MCB, MCD, MDC. You have this MEA, MEA. Now consider the equilibrium of a joint here. So after doing all this, you take a small joint. On the joint what will act? Both the moments will act in a clockwise direction. So, or rather, on the beam it is clockwise. So on the joint it will be in counterclockwise direction. So if you take the joint B, and somewhere here if you have A, and somewhere far away if you have C, this will be MBA, this will be MBC. So now you enforce equilibrium conditions. Where will you enforce? Enforce wherever we have unknown degrees of freedom. So theta B is unknown. So to determine theta B and the other unknowns, we'll enforce this equilibrium wherever we have the unknown degrees of freedom. So what is the equilibrium condition here? It is simply NBA plus MBC is equal to 0. So that's it. So to put it formally, what are the steps? So step 1, as always, is to determine the degree of kinematic indeterminacy. In force method, the first step is to determine the degree of static indeterminacy. Here, the first step is to determine the degree of kinematic indeterminacy. Why? Because our unknowns are kinematic quantities such as displacements and rotation. So first step is to determine NK and the unknowns. The second step is to write the slope deflection equations for every span. Step 3 is get the fixed end moments. So fixed end moments, you don't have to solve for them in most cases because they're available in a table usually. If you take any structural analysis book, at the back cover or the front cover, you will have a list of various loading cases and the corresponding fixed end moments. So you can either look them up or you can also solve. So in academics, we usually solve, but in the industry, while coding, it is more beneficial to look them from a table. And the last step is to enforce equilibrium equations. Now you would have already seen that we are not so enforcing equilibrium here is a very simple thing. You just have two moments and the sum of them should be 0. So this is very simple as compared to considering an entire structure, writing down force equilibrium, moment equilibrium, determine the unknown reactions. So compared to that, this is much simpler, which can be programmed in a computer. Not only that, you see that in one given equilibrium equation, only those members that are connected to that joint are participating. So at the joint B, only the span AB and BC. So basically this equation will be only in terms of theta A, theta B, and theta C. On the other hand, if you constructed the flexibility matrix by applying a unit load here, here, and so on, this will affect the displacements everywhere. A load applied here will cause displacements everywhere in the structure. So that is another benefit. So the system that we get, the system of linear equations that we get will be very sparse. So we'll get NK cross NK. We'll have theta A, theta B, and so on, which is NK cross 1 is equal to another vector This is NK cross 1. But this system, which you get, there will be a lot of zeros. It will be a very sparse matrix, and there will be a lot of zeros. So this is also computationally beneficial. So, so you can easily see that the slope deflection equations have overcome a lot of difficulties associated with the force method of analysis. Now let's get started with the problems for today. Any doubts? Okay, I assume there are no doubts. Now, before we get to the problems, we need to determine these fixed end moments, right? So as we do the problem, we'll take it to that form. We'll write it down there. So suppose in this problem, what are the loadings that we have? We have a concentrated moment here, and we have the linearly increasing loading applied here. So what we should do? We need to know the fixed end moments here. So let us determine that. So we can use any method. So first, let us consider this. Okay. So in this, we are having a mid-span concentrated moment of intensity M. Now this will generate support moments M, A, B, F, then M, B, A, F. Now how can you determine this? So this problem is anti-symmetric. What does it mean? So how will that will become clear if you see how this structure is deformed. So basically, this section of the beam, you're trying to rotate it this way. So this point has rotated this way. And here, so whatever, if you see the displacement is positive this side, it means it will be negative this side. And if the displacement is negative this side, it will be positive this side with the same magnitude. So that is what we call as an anti-symmetric structure. It will become clear when we do it systematically. So what are the, so for this structure, right? Let us draw the conjugate beam. So what does the conjugate beam look like? So the conjugate beam is something like this. So it's a fixed beam. So the conjugate beam is a free beam, and you can superpose, right? So if there was no fixed support, suppose it was just uh, simply supported with a moment, you know the bending moment diagram is something like this. So you have a moment here. The reactions will be M by L downwards on the left hand side and M by L upwards on the right hand side. So left side span will be under hogging moment and right side span will be under sagging moment. And what will be this? There will be M by L acting at L by 2. So this will be minus M by 2. This will be M by 2. So this is in the absence of the fixed end moments. Plus, you have the fixed end moments. What are they? They're like this. So now what is the condition on the conjugate beam? The slope here is 0, which means, so if this is the conjugate beam, I can replace it with a loading. This conjugate beam. This can be replaced with a loading of intensity M by EI. So I can put a by EI by EI. Here I have EI and EI. So here also I can put 2. Now this structure has to be this conjugate beam. The condition is on the real beam the slopes are 0 at both the ends, which means in the conjugate beam the shear force at A. So let us call this A prime, B prime, A prime, B prime. The shear force at A is 0, which is nothing but the rotation in the real beam, and the shear force at B is 0, which is nothing but the rotation theory. Simple. Now, how do we determine the shear force at A? It is nothing but a reaction that is coming here. So you hold this point, and then so if you have a reaction here, the shear force will be nothing but the reaction itself. But the reaction, but even before that, what is suppose this end is suppose how do you determine what will be the force here? So you take moment about this point m a dash equal to 0. So in this case, so the first one, if you see what is the moment it causes, it is m by 2 ei acting at L by 2. So it's triangular. And where does it act? It acts at 2 L by 2 by 3 from the left hand side. And it's a clockwise moment. Let me take it as negative plus the other half, right? So that acts at half m by 2 ei L by 2. And that acts at 4 L by 2 plus L by 2 by 3. So it acts at 4 by 3 of L by 2. So this, if you evaluate, you'll get find out this one. If you evaluate, you'll get. So this is 2, 4, 8, 8, 6 are 48. So you'll get but wait, so this is from this part. We also have this one, right? So again, take moment. So plus. So plus, we have a linear distribution. So it is MABF by EI to L by 2. Where does it act? It acts at L by 3 minus MBAF by EI to L by 2 acting at 2L by 3. So this is equal to 0. And if this has to be supported, so here you can see the total upward force is equal to the total downward force. But here it is not equal in general. If MAB is not equal to MBAF, the upward force and the downward force need not be equal, which means you need to have a support reaction. But if there is a support reaction, then there will be a slope that is generated in the real beam. Support reaction will cause a shear force in the conjugate beam. So if you have a support reaction, that will cause a shear force in conjugate beam, which means there is a theta in the real beam. So which is wrong. So the total upward force should be equal to the total downward force, which means MABF is nothing but MBAF in magnitude. If these two are equal, then there need not be any support reaction. So the slope condition will be automatically satisfied. Now let us determine so with that condition, the equation that we have is, so we'll get that. We'll get MABF is equal to, so if you simplify this, we get MABF to be equal to ML square by 24 EI. So here you have an L square by EI, 6 EI. So this you have MAB L square by 6 EI and this will be negative of that. So you can take it to the other side. So when you do all that, you will get MAB FL square by 6EI is nothing but ML square by 24EI, which means MABF is nothing but the applied moment divided by 4. So the values that you get are as follows. So if you apply a midspan moment of M, so this is our first result. So if you have a midspan moment applied M, the fixed end reactions will be you have, so this is clockwise M by 4 and M by 4. Just wait a minute. Yeah. So do you feel anything is wrong with this? So do you think this beam is not an equilibrium? No. The reason is this is only the applied moment, and but there is also support reactions that are countering. So it may look that the beam seems to have a net moment in the clockwise direction, but there is this shear force also in the beam. Since it is a fixed support, there is adequate shear force in the beam to overcome the clockwise moment that is generated by this panel. So that's just an aside. So for a fixed beam subjected to a midspan moment M, in the support reaction, the fixed end moments are M by 4 and M by 4, both are possible. Okay. Now, as I said, you can see the anti-symmetry. So this side, if the shear force is downwards, here it is upwards. Here, if you have a clockwise, if you have a moment that is in this direction, it is exactly opposite on this side. So here, if you have a sagging moment, on this side, you will have a hogging. And hence, the beam will deform something like this. So, something like this. So we have got one fixed end moment. And what is the other one? We have a linearly distributed load. So we need to determine the fixed end moment for that as well. So how do we do it? Step 2. Let us consider this case. You have a linearly distributed loading. How to do it? So here it is easier if we use the conjugate beam method will, so this is not symmetric, right? Note it is not symmetric nor anti-symmetric. So you cannot use any symmetry arguments to simplify this. We have two unknowns and they have to be solved for. So since we need to solve simultaneously, let us use the principle of virtual loop. Right? So let us use the method of consistent deformation to solve this problem. So how do we do it? It is very simple. The primary structure subjected to the applied loading, it deforms by d1L plus, let us apply a unit vertical force. What is this? It deforms by F11 when you apply unit vertical force, and it has rotated by F21 plus you apply a unit moment. This is scaled by x1. This is scaled by x2. So when you apply unit moment, it deflects and it rotates. So here you get, how much is this? F12 is 1, and it has rotated by F22. So what is the bending moment diagram? Bending moment diagram for this, it is nothing but m of x is equal to capital M of x is equal to so let me take the maximum value as W. It will be W by L x cubed by 6. You can check easily, it satisfies this. So here the bending moment diagram is something like this, which is negative. And here, what is the bending moment diagram? It is linear, right? So small m1 of x is nothing but, so it's a hogging moment. It's nothing but minus x. And here, what is the bending moment diagram? So the small m2 of x is given by minus 1. So let us use the usual formula that you can do. It is very simple. So f11 is integral m1 by pi dx equal 0 to L. This value you can easily see it is x squared by x squared dx, which is nothing but L cubed by 3ei. Similarly, f12 is what? It is x dx, which is L squared by 2ei. What is f22? It's nothing but L by ei. So here always, as usual, since it is a cantilever, it makes sense to take x from the left side in all the cases. So what is d1L? You can compute it easily. Just substitute this, integrate within the correct limits. You get d1L as you get d1L to be equal to W L power 4 by 30 ei, and d2L you'll get it as equal to W L cubed by 24 ei. Note that d2L is a rotation, so it has got one length dimension less than that of d1L. So this is in meters, this is radians. Now that's it. You can easily solve for this. So set up this system f11, f12, f21, f22, x1, x2 is equal to d1 minus d1L, d2L. So once you solve this, you get x2. But the way we have assumed x2 is nothing but the MCBF, right? So let me take this as B and C. So here I've taken x2 in this direction. So it is consistent with the slope deflection equations. So x2 is nothing but MCBF. Once you substitute all these values into this, right, and solve for it, it is very simple. You get MCBF is equal to W L square by 20. Sorry, W L square by 30. And then how do you get MBCF? So MBCF is nothing but, so whatever is caused here, right? So in the absence of so MBCF is nothing but just use equilibrium minus WL square by 6 due to the applied loading plus x1 into minus L plus x2 into minus 1. So we already got x2 and we have x1 as what? X1, let me give it to you. X1 is minus 9 minus 3 WL by 20. Note that it has got the dimensions of a force because it's a support reaction. It should be a force in newtons. Now substitute into this, we'll get MBCF as WL square by 20 minus WL square by 20. So minus means it's a hogging moment and it is against the sign convention that we have assumed. So for this The beam looks something like this. Have a linearly increasing loading. Support reactions that are generated are, you have in this direction W L square by 20, and in this direction we have W L square by 30. So this convention has to be taken care while writing down the slope deflection equations. Now we are completely done. Let us write down the slope deflection equations for this problem. So it is just one step and we are solved. So let us consider span AB. What is MAB? MAB is 4 EI by L theta A plus 2 EI by L theta B minus 6 EI. There's no support reaction, so forget about it. What is the fixed end moment? We got fixed end moment like this of WL square by, sorry, this is, sorry about this is the moment. So the fixed end moment was M by 4 so plus the applied moment M by 4. What is MBA? MBA is 4 EI by L theta B plus 2 EI by L theta A. Again, we got the fixed end moment in the direction, in the clockwise direction of M by 4. Just substitute the values. Theta A is 0. Theta A is 0. You get 2 EI by L. L is 4. So 2 by 4 is 0.5. So MAB is nothing but 0.5 EI theta B. M is 100. So it is plus 25. MB is nothing but let me check. So MBA is nothing but 0. So 4 by 4 is 1. So EI theta B plus again M by 4 is 25. So the correct answer is, as you can see, it is B. Sorry, C. 25 plus 0.5. This is the right answer. Now let us consider span C, span BC. So in span BC, let me go to the next page. They're asking for the member BC. So span BC, what is NBC? Is 4 EI by L theta B plus 2 EI by L theta C. There's no support settlement plus the support fixed end moment. Now we should be very careful. What is the fixed end moment at B? So we got it as, so this is what we got. We got this to be equal to WL square by 20. This is WL square by 30. So since it is in the counterclockwise direction, we need to have a minus. And MCB is nothing but 2 EI by L theta B plus 4 EI by L theta C. Yeah. Plus this moment is still in the clockwise direction, so it is positive. A plus WL square by 30. So again, as you can see, there is so here you see, so a kinematically admissible displacement field, which what is it? Kinematically admissible means it satisfies the compatibility conditions. What are the compatibility conditions? Theta B is continuous in this span and in this span. How did we enforce it? We didn't do anything great to enforce it. We just used the same unknown theta B to consider in this span and in this span. So that is done. And what are the other compatibility conditions? That the other compatibility conditions are the rotations are 0 at the fixed ends. How do we enforce it? We just drop the variable. So theta C is 0. So whatever we have is a kinematically admissible displacement field. Now we enforce equilibrium to solve for the unknown variables. So if you simplify this, just substitute the values, you get NBC is EI theta B. So 4 by 4 minus WL square by 20. So how much is W? W is 15. So 15 into 4 square. So 15 into 4 is, so how much is that? 15 into 4 is 60. So 60 by 20 is 3. 3 into 4 is 12. Minus 12. So units are kilonewton meters. And MCV is what? MCV is 0.5 EI theta B. And WL square. So 2 into 4 is, so here we have W is 50. L square is 4 into 4, 60. So 15 into 16 by 30 will be nothing but 2 into so 4. So we get 2 into 4, which is 8. So which option is that? MBC is minus 12 plus EI theta B, and MCV is 8 plus 0.5 EI theta. So it is option B. Now we are all set. We can solve the problem. What is the degree of degree of kinematic indeterminacy? So here all degrees of freedom are restrained. Here all degrees of freedom are restrained. Here it can't go up. The only degree of freedom is theta B. So let us solve the problem. So nk is equal to 1. So we'll get a scalar equilibrium equation. And the only unknown is theta B. So where should I enforce the equilibrium equations? At the joint B. So at the joint B, I have MBA and BC. So MBA plus MBC is equal to 0. What is MBA? EI theta B plus 25. So EI theta B plus 25. And what is MBC? MBC I got as EI theta B minus 12. So I can put it here. Plus EI theta B minus 12 is equal to 0. So I get theta B has some minus 6.5. Or I can just have EI on this side. EI theta B is minus 6.5. What are the units? So this is EI is in kilonewton meter square. So this is in kilonewton meters. After that, once you have determined it, what is the next step? So we have solved the problem basically. The problem has only one degree of freedom. And if we know that degree of freedom, then the complete configuration of the structure is known. So let me take this to the next. Take it to. Now what they're asking is find the absolute moments at support A and C locations. So this is again very simple. We already have EI theta B. You remember what MAB was, right? So since there is no other joint connecting at joint A, whatever moment is generated in the being AB will be equal to the moment at the support. So MA is equal to MAB in the clockwise direction, right? Assuming clockwise is positive. The clockwise moment MA is nothing but MAB. What it is? It is 0.5 EI theta B plus what was the fixed end reaction? The fixed end reaction was minus WL square by 20. So how much is that? Minus WL square by 20. Have a quick. Minus 12. Oh, sorry. Wait. It is in problem 1, right? So here it's a moment, so it is plus 25. It's nothing but plus 25. And what is MC? Is M. Nothing but MCV, which is 0.5 EI theta B plus What is the fixed and hogging moment that we got? WL square by 30, and that was equal to 8. So just substitute the values. We got EI theta V as minus 6.5. So minus 3.25 plus 25 is 21.75 kilometer meters. And this is nothing but 4.75 kilometers. So it corresponds to option D. So we have it. Now note that a lot of time in this problem was spent on determining the fixed end reactions only. If the fixed end reactions are given in a table, as it is usually done in industrial practice, we don't need to spend that time. So we just have to set up two equations, solve them, which can be programmed in a computer very easily. Now let's go to the next problem. So this is an even simpler problem. So there is no applied loading. Now you will see how fast the method is. We don't have any applied loadings. Statically indeterminate to the second degree, and it is kinematically indeterminate to the second degree. I hope you see how there are two intermediate reactions which are redundant. So NS is equal to 2. What are NK? Can anybody tell? So here you have an unknown reaction, theta V. You have an not a rotation. You have an unknown rotation, theta B. And here you have an unknown rotation, theta C. So NK is also equal to 2. So this is the first step. We have determined the degree of kinematic indeterminacy. We have identified the unknown degrees of freedom. What is the next step? Write down the slope deflection equations. So for span AB, let us write it down. MAB is equal to what is MAB? 4 EI by L theta A, but you know theta A is 0. So let us just 2 EI by L theta B. Is there any fixed end moment? No, because there is no loading in this band. But there is a support sinking. This support sinks by delta, which is 20 mm. So you see the deformed shape will be something like this. And this chord is rotating in clockwise direction, delta by L. Here it rotates in anti-clockwise rotation, delta by L. So here you will have this term minus 6 EI by L square, delta taken positive. So the span is 2 meters, so it is nothing but EI theta B minus 6 EI by L square. So 6 by L square is 4, so 1.5. And how much is delta? 20 mm. So 1.5 into 0.0002. So that is nothing but always work with the SI units. Don't get into mm. So MAB is this. What is MBA? MBA is 4 EI by L theta B plus 2 EI by L theta A, but that is 0 since theta A is 0. Minus 6 EI by L square delta. So delta is positive in this span. So take it as what you get 2 EI theta B minus 0.03 EI. Now come to span. Span BC. Span BC, what do we have? MBC is equal to 4 EI by L theta B plus 2 EI by L theta C and minus 6 EI by L square. But note that this is rotating counterclockwise, so you have minus delta. So how much is that? So 4 EI by L is nothing but 2 EI theta B plus EI theta C minus 6 EI by L square delta. We already have the value. It is the same span, so it is plus 0.03 EI. And MCB is 4 EI by L theta C plus 2 EI by L theta B minus 6ci by L square minus delta. So this corresponds to substitute the values, you will get ei theta b plus 2 ei theta c. This comes here, this comes here, plus 0.03 ei. So which option is that? The first option says MAB is 0.25, so it's wrong. And second option is EI theta B minus 0.03. Minus 0.03 EI, and MBA is 2 EI theta B minus 0.03 EI. So this is the right option. So option B is correct. Now here is the trick. So there are two degrees of freedom and two spans over which we have written the slope deflection equations. Now to determine this, we need to enforce equilibrium at the location of the 2 degrees of freedom. So the first one is the moments at the summation of all moments at the point B is equal to 0. And the summation of all moments at the point C is equal to 0. So what is the moment that is coming at C? It's only MCB, which means MCB is equal to 0. So you can replace theta C as minus EI by 2 theta B from this equation minus 0.03 by 2 EI. Now substitute this theta C in this equation. So substitute this expression for theta C, the EI theta C, in this equation you get. And what are the moments at the joint B? It is MBA plus MBC. Okay. Now MBA, MBC. This is equal to 0. What is MBA? MBA is 2 EI theta B minus 0.03 EI. What is MBC? MBC is 2 EI theta B plus EI theta C. But what is EI theta C? It is nothing but minus EI by 2 theta B minus 0.015. Check. Yeah. Minus 0.015 EI plus 0.03 EI. So plus this is equal to 0. So the only unknown in this equation is theta B. You can take everything else to the other side. And solving this, you get EI theta B is equal to EI theta B is equal to 0.015 by, so 2 into 2, 2 plus 2 is 4, 4 minus half is 3. You can cancel EI on both sides, so you get the answer in radians. And theta C we have already determined, so just plug it back into this expression, you'll get the answer. But what is asked in the question is the value of the reaction force at the support B of the beam shown in question number 4. So let me draw a free body diagram of the beam here. So we have MAB, MBA. Here we have the joint MBA, MBC. Here we have BC, MCB. And on this joint, we have this reaction. Let me call it BY. In addition, we also have the shear force in beams. Let me, in using our usual positive sign convention, it is VAB, the shear in the span AB, So that will also act equal and opposite on the joint. So here you have VAB. Here you have VBC. Here VBC downwards as per our positive sign convention. So equal and opposite shear force will also act on the joint as VBC. Now to determine By, enforce force equilibrium at joint B. So VAB plus By is equal to VBC, which implies the reaction that we want is VBC minus VAB. Now, how to determine VBC and VAB? Consider the individual spans one at a time. So, if you enforce moment equilibrium for the individual spans, you get MAB plus MBA plus VAB, which is separated by L, is equal to 0, which means VAB is nothing but minus MAB plus MBA by L. Similarly, VBC is nothing but minus MBC plus MCB by L. So as a result, if you substitute this into the expression for By, we get By is equal to MAB plus MBA minus MBC plus MCB divided by L. So substitute all our values into this. We already got MAB as MAB. What is MAB? MAB is EI theta B minus 0.003 EI. So let us determine the numerical values. MAB is EI theta B, and EI theta B itself is 0.015 by 3.5 EI minus 0.03 EI and what is MBA? MBA is half of this, double of this, 2 times 0.015 EI by 3.5 minus 0.03 EI. MBC is can substitute into this 4 EI by NBC, you can substitute from this. So it is 2 times theta B. So 2 into plus EI theta C. Right? So EI theta C, we have this expression. Plug it in. So minus 0.5 theta. Minus 0.03 by 2 EI. So this is done. Then the last term is plus 0.03. You get plus 0.03. What is MCB? Since it is a hinge term, it is 0. So substitute in this expression for By. Paste it here. So substitute these expressions for the moments into this expression with L is equal to 2 meters. Upon substituting them, the value of By that you get will be minus 0.0342856 EI. And note the negative sign. So negative means we assume upward reaction as positive. So on the beam, we have a downward pull. So on the beam, on the joint, we have a downward pull. That is obvious since the support is sinking downwards, it has to pull the beam downwards. It's not supporting a load on top. So, and if you substitute the value of EA, you get minus 0.0342856 into E is given as E is given as 100 kilonewton per mm square and I is 5 into 10 power 7 mm per cube. So convert it. So E is 100 kilonewton per mm square. So we can make it kilonewton per meter square. So to make it meters, we get this into 10 power minus 6 into square into 5 into 10 power 7 mm per cube. So we get into 10 power minus 5 into 10 power 7 mm per cube. So mm gets cancelled and we have already divided by L everywhere. So you will get this to be equal to minus 171.4 kilograms. So the answer is option D. Let's go to the next problem. Choose the correct bending moment diagram for the beam of fusion 4 from the figures given below. So to get the bending moment diagram, we need to find out what is the moment at the point B and the moment at the point A. So the moment at the point B is nothing but, so this is the joint B, and on the right span, we take clockwise moments as positive. So at the joint B, MB is nothing but minus MBC. So clockwise moment means it is hogging at this point. So it is equal to minus MBC or it is equal to MBA. This is MBA. This is MBC. If we take sagging moments to be positive, then as per this convention, MB is equal to minus MBC or it is equal to MBA. And MA is nothing but MAB. So that is simple. So let us determine what is MBA. MBA is equal to, use this expression. So we already have this. So just evaluate this. This turns out to be, let me put it here, 0.015 by 3.5. So MEB is equal to minus 128.57 kilonewton meter. And this is equal to 2 into. This is equal to 107 minus 107.14 kilonewton meters. So let us take these values. So MP is minus 107.14. And AB is minus 128.304. Is so this is the joint. This is MBA. And here it is MAB. So MBA is negative. That means it is not actually hobbing. So it means it is sagging. So actually this is positive. And MAB negative means it is not sagging and it is hogging. So at the joint C, the moment is 0. At the joint B, it has a sagging moment of 107.14. So this is 107.14 positive. And here it is minus 128.57. So as per this convention, we have the correct answer is option B. Note that it is the same except that the direction of positive and negatives are interchanged. This is minus, this is plus. It has followed the same profile. Now let us go to the next problem. So choose the correct slope deflection equation for the following beam under the given load conditions. So here we have a 3-span continuous beam. As usual, let us determine the degree of static indeterminacy. So kinematic indeterminacy. So NK is nothing but. So here you have a rotation theta B. theta C, theta D. Since this is not supported, this can also reflect this way. So you have a delta here. So it looks like it has a kinematic indeterminacy of 4, which is too high to solve on paper, but it actually doesn't. How do we simplify the problem further? Consider the span CD. So if you consider the span CD, it has MCD and MDC. But what is MDC equal to? MDC is nothing but 10 kilonewtons meter, which means MCD is also equal to minus 10 kilonewtons meter. Why is that so? Simply enforce equilibrium. There is no there's no force acting on this span, so MCD is equal to minus MDC, which is minus 10 kilonewtons meter. So when it comes to the other spans A, B, and C, you can replace MCD by minus 10 kilonewtons. Not only that, now enforce equilibrium of moments at joint C. What do you get? MCB plus MCD is equal to 0, which means MCB is equal to 10 kilonewtons meter. So this is one condition. And now note that MCB, as I said, will depend only on theta C and theta B. So this will depend only on theta C and theta B. And the other spans, MBC, MBA, MAB depends only on theta A and theta A, theta B, and theta C. And out of that, theta A is 0. So it depends only on theta B and theta C. So to solve this problem, we have reduced it from 4 unknowns, which are theta B, theta C, theta D, and delta CD. By applying one equilibrium equation, we have reduced it to a problem of just 2 unknowns, which are theta B and theta C. So this can be solved easily. Now let us write down the slope deflection equations for each span. So for span AB, there is a uniformly distributed load up to half of the span, and the rest is not loaded. So the first task is to determine the fixed end moments for this span. So before that, MAB is equal to 4 EI by L theta A. Since theta is 0, it is just 2 EI by L theta B. There is no chord rotation, there is no settlement, support settlement, plus MABF. What is MBA? MBA is 4 EI by L theta B plus MBAF. And now come to span, so this is span AB. Coming to span BC, you have a point load at the middle. So MBC is equal to 4 EI by L theta B plus 2 EI by L theta C plus MBCF. And MCB is equal to 2 EI by L theta B plus 4 EI by L theta C plus MCB. And we are not considering the span CD because we have already taken its effect as a moment applied onto the span BC in the direction MCB, which is 10 kilonewtons meter. Now the next step is to determine the fixed end moments. So let's get back to that. Fixed end moments. We have, in the first case, we have this span loaded up to half of it by a uniformly distributed load of W. So let me consider a primary structure like this. I have released the end moments And this results in a primary structure, which is a simply supported beam, which is statically determinate and stable. Then let us apply the redundant moments on the primary structure, so which are this MABF and this MBAF. So let us call this variable as x1 and this variable as x2. As usual, using the principle of virtual work along with the method of consistent deformation, we can determine these quantities x1 and x2, which directly gives the values of the fixed end moments at these two supports. So let us determine. So the bending moment diagrams are as follows. So the support reactions due to this applied loading will be, so the total load is WL by 2. It acts at L by 4. So to the support we have 3/4 of WL by 2. Into this support you get 1/4 of WL by 2. So the bending moment diagram for the applied real loads is given by the expression. So 3/4 of WL by 2 is 3WLX by 2 minus WX squared by 2. So it's a parabola, but it's not symmetric about the center line. So it is something like this. And this is valid only in the region 0 less than or equal to x less than or equal to L by 2. After L, x crosses L by 2. X is taken from the left hand side. So when x is greater than L by 2, you don't have the distributed loading continuing. So beyond that, it is just linear. So it is 1/4 WL by 2 acting at L minus x, and that is also a sagging limit. So it is 1/8. This is 8. 3WLX by 8. 1/8 WL acting at L minus x. So this is L by 2 less than or equal to x less than or equal to L. And this moment is sagging. What is that for the? This itself is equal to x1 times this structure plus x2 times this structure. So for the redundant structure one, the bending moment diagram is very simple. We have an applied moment of 1 here. So there will be equal and opposite reactions. 1 by L and 1 by L. So something like this. Sagging moment of intensity. Maximum bending moment is 1. So M1 of x is given by 1 minus x by L. So as x is approaching L, M1 goes to 0. This positive. Let me redo this. This plus the third case where we have an applied moment of 1 kilometer this side, but it is foggy. So here it is negative, but with the same slope of 1 by L. So M2 of x is just minus x by L. Now the rest of the procedure is as usual, simple. So what is F11? F11 is integral M1 of x, M1 of x dx by EI. So it's easy to see that this value is nothing but L by 3 EI F12 is integral m1 of x, m2 of x by ei dx. So these integrals are from 0 to L. And this is equal to, so this is positive and this is negative. So you get a minus L by 6 ei. And F22 is integral 0 to L. It is the same as the above. It is the same as F11, just it is just the squared area of area under the square of this curve. So it is the same as F11. 0 to L. M2 of x the whole square by E. Yes. So this is just L by CL. Now once we have determined these, the next step is to determine D1L and D2L. So what is D1L? D1L is integral 0 to L capital M of x, M1 of x dx by EI. But note that capital M of x has got two different definitions in the two halves of this span. So you need to split the integral from 0 to L by 2. So from 0 to L by 2, capital M of x is defined as 3WL x by 8 minus W x squared by 2. And what is M1 of x? It is 1 minus x by L dx plus integrals L by 2 to L. And here it is defined as WL by 8 into L minus x multiplied by 1 minus x by L dx. So you can evaluate this integral and it turns out to be, it's a polynomial, although it looks long, it flips up into a polynomial and can be directly integrated. And the value of D1L that you get is 3WL cube by 128 EI. Similarly, D2L is integral 0 to L M2 of x, M of x by EI dx. And M of x has the definition of M of x is piecewise. So split the integral from 0 to L by 2. What is M2 of x? Minus x by L. Okay, it's minus x by L into 3WLx by 8 minus WX squared by 2. There's an EI everywhere. Just take care of it. Dx plus integral L by 2 to L minus x by L WL by 8 L minus x dx. So this can be integrated easily. It's a bit long, but you can do it. And this value turns out to be D2L turns out to be minus 7WL cube by 384 EI. You can check it. Now, what is the system that we need to solve for? So the system that we get is F11, which is L by 3 EI. F12 is minus L by 6 EI. F21 is minus L by 6 EI. And F22 is L by 3 EI. Our redundant forces are the fixed end moments themselves. So here we have MABF. Here we have MVAF. Is equal to minus of the D1L and D2L. So here we have minus 328 by minus 3 by 1.8 WL square L cube by EI. Here it is 7 by 384 WL cube by EI. So solve the system of equations, then we get MABF is equal to minus 11 by 192 WL square, and MBAF is equal to 5 by WL squared, 5 by 192 WL squared. So it's like this. We have a fixed beam with half of the span loaded by a uniform load of intensity W, and it generates fixed end moments. So minus means it is hogging this counterclockwise. WL squared, 11 WL squared by 192. And this side you have 5 WL squared by 192. So that is done. So this is the case 3 that we have looked at. And now we have a point load. So we need to determine the fixed end moments corresponding to a point load as well. That is much simpler than this because of the symmetry that is involved. This number 4. You have a point load applied onto a fixed beam. Let the point load of be of magnitude P. So the beam is symmetric, which means the fixed end moments will be equal and opposite. So here, if you have a moment MAB, so this is in the anti-clockwise direction. So this is minus MABF. Here you will have MBAF. So the relation is MABF minus MABF is equal to MBA. So let it be equal to some value, say MF, fixed end moment. Now using the conjugate beam method, you can draw. So the fixed beam becomes a free beam, the free conjugate beam. So the bending moment due to a midspan point load is like this. So let us load the structure by the M by EI diagram. So we know that the maximum moment is PL by 4 EI. And let us superpose it with the effect of the fixed end moments. So fixed end moments are equal and opposite, so it will be a constant distribution. Apply downwards. MF by EI. What is the condition? So the condition is the slope on both sides of the beam is 0. So the real beam theta A is equal to theta B is equal to 0, which corresponds to, in the conjugate beam, the shear force at the point A prime is equal to the shear force at the point B prime, and both are 0. So when does the shear force arise? The shear force arises if there's a reaction, and the reaction is required if the loads are not self-equilibrating. The force, if the total upward force is equal to the total downward force, then there is no need of, and if the moments are balanced, there is no need for the support reaction. So the moments will be balanced since the loading is symmetric, but the force, in order for the forces to be balanced, we can equate the areas under the loading. So area under the applied loading, a moment due to the applied loading is half into L by 2. Half into L into PL by 4 here. That is equal to MF by EI into L. So L, EI you can cancel in all sides. You get MF is equal to PL by 8. So the fixed end moment due to an applied point load is PL by 8. Well, let us go ahead and write down the slope deflection equations for this problem. So this is nothing but MAB is nothing but 2 EI by L theta B. 2 EI by L theta B. What is MABF? MABF we determined it to be minus 11 by 192 W L square. This is equal to 4 EI by L theta B plus 5 WL square by 192. And similarly, MBC is nothing but so MBCF is nothing but minus PL by 8, and this is PL by 8. So let us just plug in the values. The values that we get are the MAB is, so the spans are all 4 meters. So MAB is 0.5 EI minus, so W is 24. 24 by 192 is 1 by 8. L square is 4 square 16. So 16 by 8 is 2. And 2 into minus 11 is minus 22. And BA is equal to EI, sorry, there's a theta B, EI theta B. 5 WL square by 192. So WL square by 192 is 24 into 16 by 192, which is 2 plus 10. So this is 10. And MVC is 4 EI by L. So that is EI theta B plus 0.5 EI theta C. This is PL by 8. P is 24. 24 into L is 4. 4 by 8 is half. So half of 24 is minus 12. And MCB is 0.5 EI theta B plus EI theta C. This is plus 12. So these are the slope deflection equations for these two spans. So let's see which option it is. So this is option A. Let's go to the next problem. So this is the problem of a frame structure. So here it is slightly different from beams because this can have a, and there are more number of joints framing into a, there are more number of beams framing into one joint. That is one difference. And this can also have a sway. So sway is when the structure has a relative horizontal displacement, a global horizontal displacement. But if it is sufficiently restrained, it will not sway. So this is a non-sway frame. There is no side sway. Why is it? Why is that there is no side sway? You can see. If you assume the members are axially inextensible, which we are assuming, so if you assume the members are axially inextensible, the joint B is not going to move towards the right. Joint C, although it has got a roller, it cannot move because the member BC is inextensible. Similarly, joint B cannot move down also because the member BD is inextensible. So we can quickly write down the force displacement slope deflection equations for this. Before that, let us determine the degree of static and kinematic indeterminacy. So the degree of static indeterminacy is very high for this problem. It is 1 plus 3, which is 4. But the degree of kinematic indeterminacy is 2. What are they? It's theta B and theta C. Here you have a rotation theta B. Here you have a rotation theta C. You can also have a displacement delta if it is not actually rigid. Since it is actually rigid, you cannot have a delta C or delta B. So let us write down for span AB. The slope deflection equations are as follows. You have 4 EI by L theta A, which is 0, plus 2 EI by L theta B minus, so we know at this point we get a moment of minus PL by 4. So minus 50 into, let me write this, minus PL by 8 is equal to 0. There is no sway, so the relative displacement delta is 0. Let us substitute the values. So the span is 5 meters long. So 2 by L is 0.4 EI theta B, and P is 50. 50 into 5 is 250. 250 by 8 is 31.25 minus 31.25. This is so this is the moment MAB. What is MBA? MBA is 4 EI by L theta B. So 4 times 4 by 5 is 0.8. So 0.8 EI by L theta B. And here the fixed end moment is plus PL by 8, which is 31 point. Similarly, let us look at span BC. So in span BC, MBC is 4 EI by L theta B. So 4 EI by L is 0.8 EI theta B plus 0.4 EI theta C. There is no fixed end moment and there is no settlement of the supports. And what is MCB? MCB is 0.8 theta C plus 0.4 theta B into EI. But note that C is a hinge joint, so MCB is equal to 0, which means theta C is nothing but minus theta B by 2. As a result, MBC becomes, so MBC is nothing but let me check. 0.4 minus 0.2, so it is 0.6 EI theta B. So this is the slope deflection equation for this span. Now let us look at span BD. Or rather span DB, because the load is applied when you, in order to be consistent with the convention of the rotation, you need to look this way so that the load acts downwards. So subjected to a uniformly distributed loading, we need to determine the fixed end moment. Let's do it. So that is also simple because of the symmetry of the problem. This is the final one for today. We have a uniformly distributed loading of intensity W. Span is L. So very simple. Again, because of the symmetry, you can say the fixed end moments will be equal and they will be equal to sum minus MF plus the distribution, the bending moment distribution due to the applied loading is WL squared by 8. Maximum value is WL squared by 8. And the profile is given by N of X is equal to W by 2 X into L minus X. Now let us consider the conjugate beam. So the conjugate beam is a free beam. So it's a free beam loaded by the positive bending moment. And the negative bending moment. So the compatibility condition is that the slopes on both ends of the beam should be 0. The slope in the real beam is the same as the shear force in the conjugate beam. The shear force has to be 0, then there shouldn't be any support reaction. And if there shouldn't be any support reaction, then this loading should be self-equilibriating, which means the total upward force should be equal to the total downward force. So the total downward force is MF L by EI. That is equal to, so the area of a parallelogram is 2/3 of that of a rectangle. So 2/3 L into WL square by 80. So equating both, what we get is the fixed end moment is equal to WL square by 12 EA. And we can easily see it should be hogging on both sides of the beam. So the convention is like this. For this beam, M AB F is nothing but minus WL square by 12. There's no EI. Here it is fogging. So it is MBF is equal to WL square by. So this is the last result for the day. So the span DB. What is MDB? MDB is equal to 4 EI by theta D, but theta D is 0. So 2 EI by L theta B. And it is a non-sway frame. And the fixed end support reaction that is generated is minus W L square by 12. So the length of the beam is 4 meters. So it is 0.5 EI theta B. Sorry, it's not 2 EI by L. So 2 EI, this beam has got a moment of inertia of twice the other beam. So it is 2 times 2 EI by L. So it is 2 into 2 by 4, which is 1. So this just EI theta B. W is 30, length is 4. So 30 into 4 is 120. So 120 by 12 is 10. 10 into 4 is 40. So minus 40. And what is MBD? MBD is equal to 4 EI by L theta B. So 4 into 2 EI by L theta B plus WL square by 12. So this is 8. 8 by 4 is 2. So 2 EI theta B plus 40. So therefore, we have the slope deflection equations for all these spans. Let us see which option is correct. So the correct answer is MBA is 31.25 plus 0.88 EI theta B, and MDB is minus 40 plus EI theta. So the correct option is option D. Now, at which point we need to enforce? So at which point we need to enforce the equilibrium equations at all unconstrained degrees of freedom. But note that we have already enforced the But note that we have already enforced the equation of equilibrium at the joint C to determine theta C in terms of theta B. So we cannot do it again. So the resulting system is just a scalar system, 1 by 1. So just set sigma MB is equal to 0, which means MBA plus MBC plus MBD is equal to 0. So what is MBA? So let me write it down directly. The system that you get is MB. This is 0.8 and MBC 0.6, so 1.4. 1.4 plus 2 is 3.4 EI theta B. Plus we have at the 40 plus 31.25 plus 71.25 is equal to 0. So theta B evaluates to, or EI theta B evaluates to minus 20.955. So that is it. Now the next question. We are asked to determine the moments at the joints A and D of the frame. So we have got EI theta B as minus 20.955. Now M A is nothing but MAB. But what is MAB? MAB is 0.4 EI theta B minus 31.25. So just substitute into this, we get MAB is minus 39.63 kilonewtons. What is MD? MD is MdV, which is 2 MdV EI theta B minus 40. So it is EI theta B is again minus 20.955 minus 40. So it is minus 60.955. So MA is 39.63 and MD is 60.963. The correct answer is option A. So we are at the end of today's session. We have solved all the problems. So you can, if there is any doubt, you can post in the comments or in the course webpage, the announcement section. I hope you can go through all these and then it will be helpful for your Wednesday's assignment. So thank you everyone and good luck for the assignment.